This is a review of the solutions for quiz number 4. The first question had a general picture of a 1.5 kilogram mass inclined on a 35-degree angle of incidence ramp um, with a tension force applied 20 newtons up the ramp, and mu sub s, coefficient of static friction, equal to 0.5, mu sub k, coefficient of kinetic friction, equal to 0.3. And just for easy numbers, g is equal to 10 meters per second per second. So you were asked in part A to draw a careful free body diagram, and here's my rendition, including a coordinate system. And so the downward weight, vertically downward, is a 1.5 times 10, which is 15 newtons. And this angle theta here is the same as the angle theta where my cursor is. And therefore I can break the mg into mg cosine theta, the component perpendicular to the plane, and mg sine theta, the component parallel to the plane. And so doing this with mg makes all the forces, and if you count these as two forces, there are 1, 2, 3, 4, 5 separate horizontal and parallel forces. All of those will either be aligned with y or aligned with x. Okay, so moving to the second question, B, write Newton number 2 in the y direction consistent with your coordinate system. Okay, well, what I've done with my coordinate system is I've oriented y up, and I've oriented x horizontal and up to the plane. And so based on y being up, I have a positive force, that's n, and I have one negative force, mg cosine theta, and therefore my Newton number 2 in the y direction is n minus mg equals cosine n minus mg cosine theta is equal to 0. There's no acceleration in the y direction, and therefore the forces have to add to 0. And so let's see if I go over here and just and go down. So the next thing to do was to write an equation, Newton number 2 in the x direction, consistent with, again, with the coordinate system, of course. And to do that now, there is one force in the positive direction plus t minus mg cosine theta minus the frictional force, and that's what you see here. And so this is the net force up the plane is equal to the mass of the object, which is times m times a sub x, where x is the a sub x is the acceleration up the plane. And I'm assuming here that f sub f is down the plane, and that therefore a sub x is up the plane. And so that might have to revise that based on what happens later, but tentatively that's what I'm going to assume. Okay, so now part D, find the normal force. Well, the normal force from part B is just mg cosine theta, which for this problem is 15 newtons times the cosine of 35. In other words, it's 12.29 newtons. Part E asks you to determine whether m is stationary, moving up the plane, or moving down the plane, and the answer is it's moving up the plane. And the reason you know that is if you calculate t minus mg sine theta, that's going to be 20 newtons minus 10 newtons times the sine of 35, which works out to be 11.4 newtons. And then if I look at mu sub s times n, which is the maximum static frictional force possible down the plane, that's 6.15 newtons. And since the force up the plane is bigger than the maximum frictional force down the plane, it's going to be moving up the plane. Okay, so a sub x is indeed moving up the plane, and I did choose f sub f to be in the right direction. What is the frictional force acting on M? Okay, so frictional force, since we've determined it's moving, the frictional force is mu sub k times n. Mu sub k is zero point 0.3 in this problem. N has already been determined to be 12.29, and so you have a 3.69 Newton force that's a typo, down the plane. Okay, so please note the typo. My apologies. And then part G is what is the acceleration of m? And so we simply take Newton number 2 in the x direction, divide by m, and you plug in all the numbers. And so it's going to be 20 newtons minus 1.5 kilograms, 15 newtons times the sine of 35 degrees minus the frictional force, which is 3.69 newtons, divided by 1.5 kilograms. And so the numerator is 7.71 newtons. That's the net force up the plane, divided by 1.5 kilograms. And the acceleration up the plane is 5.14 meters per second per second.